Good morning, ladies and gentlemen. Today we're going to look at finding the derivative and the integral of log functions. So to start off with, this first video will just be the mechanics of it, and then the second video we'll look at the applications of calculus involving logs. So I guess the most important thing to remember is this here. In that box gives us the function and its derivative. Essentially, if you find the derivative of ln x, you get 1 on x. And the assumption here is that x is greater than 0. Not greater than or equal to, but strictly greater than. And it's because we can only log positives, so therefore the derivative is only valid for when the original function is valid also. Note that if you do ln of f of x, the derivative comes out of f dash of x on f of x. And the other way of thinking about that is it will have come from 1 on f of x multiplied by the derivative of the inner, in this case here the inner being f of x, so f dash x. And that simplifies to what they've got written there. So really it's an application of the chain rule is what gets us the log of a function. Also note, this logic works backwards as well. So we know that we can go from 1 on x back to ln x by integrating. So the integral of 1 on x dx is equal to ln x plus c for x greater than 0. Now, I put a recall the log laws down there because we'll need them in a second. There are two other things I'd like to draw your attention to. The first one is possibly beyond the course. It's an integral of 1 on a linear. And the derivative of that, 1 on a, ln, the modulus of ax plus b. Modulus means that in there is only going to be the positive of it, because we can't log a negative, plus c. And then almost certainly beyond course, note up here, I didn't tell you how to integrate ln x dx. The integral of ln x dx is x ln x take x plus c. The proof is well beyond the course, however, it might be worth just having these two down somewhere subtle in your reference book for use later on with some harder questions. Alright, so let's look at this in practice. ln of, and that there, we can think of the internal function as f of x. So the derivative of this will be 1 on the original function multiplied by the derivative of the inner function, in this case 2x. And you wouldn't really need to write that intermediate step, you can just leave it as 2x on x squared plus 1. And often there will be opportunities to simplify your final answer, but here there is none. There's no common factor and there's no way we can factorize to pull out a common factor. Alright, here, integrating, which is fine. Different note to differentiating before. And remember, what worked in calculus previously for us still works. So previously in calculus we were a big fan of chunking it, and that's exactly what we're going to do again here. The integral of this is the integral of 3e to the x dx plus the integral of 1 on x dx. Doing them by parts, the integral of 3e to the x is very simply 3e to the x plus this here is ln x. Then we remember the c that catches people. Remember to add the c on, because it's an indefinite integral. Alright, here we're finding the derivative. So the derivative of ln x is 1 on ln of x multiplied by the derivative of the inner function. So this has the potential to get a little messy. The idea is you approach it nice and systematically. And by systematically, I would think about taking the inner function first. Now the inner function, we need the derivative of that. So the derivative of the inner function is clearly coming from a quotient rule. So u and v. This is x squared plus 2x, and here is x take 5. U dash is 2x plus 2. V dash is relatively easy at 1. Alright, and then we're looking at the derivative of this. uv dash, which is x squared plus 2x, take u dash v, put this bit in brackets, 2x plus 2 bracket bracket x take 5, divided by v squared, x take 5 squared. And then, once we've got that off to one side, we can use it to calculate the main derivative. So the main derivative is that on top of 1 divided by this. So it looks like, that's terribly explained, but it looks like 1 on x squared plus 2x on x take 5 multiplied by everything in this bracket here. Okay. Now, if you were asked to find the derivative without simplifying, that would be as far as you'd have to go. If you want to go a little further, then this bit here would go up there. It would end up cancelling with one of the powers down there. There are certain things you can do. You can expand and simplify the top and look to keep going. But in reality, that's as far as we'd expect you to go. Alright. This here is possibly beyond the course because it uses the chain rule twice. So up here, there was just one inner function, which we could use the chain rule on to find the derivative of the inner. Here, effectively there's two inner functions, but because we've taught you the chain rule, I would expect you to apply it multiple times, and this is where the harder level questions get from. So I would, first of all, recognize that you can let t equal cos of 2x. And whenever you let t equal something, it's probably worth finding dt as well. Therefore, dt is equal to minus 2 sine of 2x. So the derivative of cos minus sine throws out the derivative of the inner, which is sort of the second inner chain rule. And then what we have is ln of t cubed. So if y is equal to ln of t cubed after this substitution, therefore dy dt is equal to the derivative of this multiplied by dt. So let's find the derivative of this. Well, the derivative of this is 1 on t cubed multiplied by t squared, because that's the derivative of the inner. So t squared on t cubed times dt. Now, if you want, we can either simplify it here or simplify it after the replacement back. I would say simplify it here, makes it look nicer. T squared on t is 1 on t times dt, and that is dy dt. Now let's change it over to dx. So what we're going to do here is grab that, and remember we found it already, it's there, and make the replacement. So t is 2 cos x, so dy that's still dt. Dy on dx is 1 on cos 2x multiplied by negative 2 sine of 2x. And we could write that as a single fraction with this portion up here, and we wouldn't be looking to do any other further simplification. Note that if it was cos on sine, we could write that as some sort of tan x. Even right now, we could write it as 1 on tan of 2x. But there would be far enough. Alright, they are some basic examples and then a harder one. The important thing to remember is these notes here, highlighted in yellow. Alright, thank you very much. I'll see you in class.